Welcome to 54th lecture in Industrial Engineering and Operations Research, and we are discussing operations research. In operations research, very important topic of queuing theory. Already we have conducted 3 lectures on this topic, and this is a small 4th lecture. We told you some theory and we also did exercise problems. Okay. So, I will concentrate on single server models. Although in the previous classes you have done some problems on the multi-server models also, but here we will concentrate this one because most of the exams in the syllabus only single server model is there. So, it is important that it should be strengthened. It should not be that in the process of learning so many things you are not able to do the basic question. So, that is why we will discuss single server model in detail here. So, a single server model in queuing theory refers to a system where one service facility or server handles incoming customers one at a time. So, we assume that customers do not arrive in batches. One customer only arrives at one time, and similarly they are serviced also one customer at a time. It is the most basic and widely studied queuing model, represented by Kendall's notation. In Kendall's notation, the format is A/S/1. So, we say A is the arrival process, S is service time distribution, and 1 means single server. So, we simply say 1 here, server is only 1. So, most common among them is MM1, that means very totally random arrival, totally random service. So, that means M means Markovian, basically we say Poisson arrival. Poisson arrival is represented by Markovian also, and if the arrival is Poisson and exponential is related, but here we say Poisson arrival, that means arrival happens as per Poisson distribution and service happens as per exponential service, and there is a single server is there. So, we say that for Poisson arrival we use symbol M, Markovian, and for exponential service also we use symbol 1. So, we say M/M/1Q. Applications are many problems can be made. Same way bank teller or ATM. In ATM you do one customer is only served by one. If there is only one ATM, you go and stand in the queue. Doctor's clinic with one doctor, call center with one line. These are the examples. So, single server, non-exponential service time distribution and unlimited queue can also be there. In queuing system, service times are often assumed to follow an exponential distribution. However, in some real life situation, service times do not follow this pattern. The normal distribution can be a useful alternative. So, in such queuing model where arrivals follow Poisson process and service time follow normal distribution depends on standard deviation for service time. So, we know the standard deviation. So, suppose single server, non-exponential service time distribution, unlimited queue. I am not giving to give the complete derivation, but you know these are the formula. The performance measures are determined as P0 is equal to 1 minus lambda by mu. Here P0 is there, that probability that system will be empty or there will be 0 customer in the system, that is 1 minus lambda by mu. It was in other case also, that means exponential service time distribution also, but LQ formula is different. LQ is equal to lambda square, lambda is the arrival rate, sigma square, sigma is the standard deviation of the service, plus lambda by mu whole square divided by 2 1 minus lambda by mu, and LS is equal to LQ plus lambda by mu. This was common that formula. WQ, it is Little's formula. WQ is equal to LQ by lambda, by Little's formula. Okay, Little's formula, you never forget this, Little's formula. It is very little size, but it is not because of that. Little was the person, that author's surname, and WS is equal to WQ plus 1 by mu. This is also understood that it is like this. Now what happens? Let us do the example of one problem, single solver but non-exponential service time distribution and unlimited Q. That means Q can be as big as possible. Example, at a shop, customers arrive at a mean rate of 5 per hour. So customers are served at a mean rate of 6 per hour. You understand that in single server model, your service rate will be more than the arrival rate. Otherwise, the Q will become unstable and all these formulae will not work. So here you have to assume that you have to, if the problem should be of that type, that here service rate is actually 6 per hour, whereas arrival rate is only 5 per hour. The service time has a standard deviation of 0.06 hours. Suppose this is the standard deviation in the service. Okay, so that means okay, you can find out that what is the service time. Service time will be 1 by 6 hours. In 1 by 6 hours, there can be this much standard deviation. So the question is that determine expected number of customers in the queue, expected number of customers in the system, expected waiting time in queue, expected waiting time in system. So how do you do that? You have to say lambda is equal to 5. Actually, more precisely, we have to write unit. So 5 per hour. So you can say 5 H inverse per hour. Mu is equal to 6 customers per hour. So see, this is also H inverse, and arrival rate, and sigma is equal to 0.06. This is 0.06 hour. Okay. So you have to find out LQ. LQ is equal to, formula is given, lambda square into sigma square plus lambda by mu whole square divided by 2 and minus lambda by mu. Lambda is non-dimensional. No, not lambda is not non-dimensional. Lambda is 5 customers per hour. So this is square and this is H square. So lambda square into sigma square will become non-dimensional, and plus lambda by mu. So lambda also has same unit 5 per hour and this is 6 per hour. So this will become non-dimensional. Two non-dimensional quantities can be added. These type of checks also you should do time to time, so that you don't do a mistake. So LQ is equal to this much divided by 2 and minus lambda by mu, and now you substitute the value 5 square, sigma is equal to 0.06. So 5 square into 0.06 square plus 5 by 6 square, 2 1 minus 5 by 6 is equal to 2.35. So therefore 2.35 customers in the queue. Expected number of customers in the system, LS is equal to LQ plus lambda by mu, that means 2.35 plus 5 by 6, that means 3.18 customers in the system. Okay. You should not say that LS is equal to 2.35 plus 1, that means 3.35. It is only coming less only. And then so this will be now expected waiting time in queue. Use the Little's formula, you know LQ, so you can find out WQ. WQ is equal to LQ by lambda, that means 2.35 by 5, and this is equal to 0.47. And expected waiting time in the system is equal to WS is equal to WQ plus 1 by mu is equal to 0.47 plus 1 by 6, that means 0.64. So these are the type of formulae we have written, and this is the thing, expected waiting time in system. Now it is unit. Okay. So what should be unit? LQ was customers and lambda was 5. but 5 was what? Per hour. So, this will be hour. You have to say expected waiting time in the system WQ. So, this is hour, and 1 by mu 1 by 6, that is also hour. So, this will be 0.64 hour. Okay. So, you have to write the full answer, otherwise you will not get the marks, that you have to say with hour. Now, single server constant service time unlimited queue. Suppose it is constant only, that means there is no normal distribution, that means sigma is equal to 0. So, queue type can be single server queue with unlimited waiting capacity. Arrival pattern is typically modeled using a Poisson process, random arrivals. If it is a fully random way, then Poisson distribution suits. Mathematically, it can be proved that it is Poisson distribution. Service time is equal to constant, which is called deterministic, meaning every customer is served in exactly the same amount of time. Okay. And notation represented as M/D/1 in Kendall's notation. M means what? Markovian. D means deterministic. So, M means Markovian or Poisson arrival, D means deterministic or constant service time, and 1 means there is one server. Applications is used where service processes are highly automated or mechanized. It is fully automatic type of thing, like ticket vending machine, automated toll booths, that you know it is same. So, in that case, for constant service time, standard deviation sigma is equal to 0. So, you can substitute sigma is equal to 0 there. In the same formula, LQ is equal to this much length of the queue when service time is not constant, and the length of the queue, suppose you put sigma is equal to 0, then you get LQ is equal to this much, and it has come lambda by mu square 2 or minus lambda by mu, and LS is equal to, of course, LQ plus lambda by mu. By Little's formula, again you calculate WQ is equal to LQ by lambda by Little's formula, and WS is equal to WQ plus LQ by lambda. Okay, this is not LQ by, this is WQ plus waiting time. Okay, so that means you can say waiting time in the this one. So, LS is equal to this one. So, it should be, okay, this has to be corrected, WS by Little's formula again, WS is equal to LS by lambda. You have to say LS by lambda. Okay. So, LS by lambda will become LQ by lambda plus 1 by mu. Okay. So, this is a plus 1 by mu. So, LQ by lambda is basically WQ. So, WQ plus 1 by mu. So, therefore, this formula is actually WS is equal to WQ plus 1 by mu. Okay. So, this is what this one. Now, let us solve one example. At a recycling facility, truck drivers delivering plastic materials currently experience an average waiting time of 10 minutes before unloading. So, they face that average waiting time of 10 minutes. The cost of idle time, that means time wasted in queue for both driver and truck, is rupees 300 per hour. That means unnecessary 300 per hour just goes. Okay. Management has decided to install a new unloading device that would process truck loads at a constant rate of 10 trucks per minute, okay, per hour. That means it will take now 6 minutes instead of 10 minutes, with an operational cost of rupees 15 per truck unloaded, but operational cost will be 15. Truck arrivals follow a Poisson distribution with an average arrival rate of 8 trucks per hour. Is the new unloading system profitable? That is the question, decision making. So, the solution is that waiting time waiting cost is equal to waiting time into cost of waiting. So, waiting time is how much? 10 minutes and 10. So, that means in hours it is 10 by 60, but per hour cost is 300. So, 10 into 60 into 300, that means rupees 50. Okay. So, that means waiting time is basically he faces that 50, okay, rupees 50. In new unloading system, mu is equal to 10 and lambda is equal to 8. So, mu is equal to 10, actually better to write the units also here. Mu is equal to 10 minutes, this one. So, here 10 trucks per hour, okay. So, 10 trucks per hour. So, we say per hour, or you can say hour H inverse. Lambda is equal to basically already given that 8 customers arrive per this one. So, suppose 8 trucks per hour, okay, average arrival rate is 8. So, that is why it will become 8 per hour. So, formula wise WQ is equal to LQ by lambda, and this is 1 by lambda. LQ formula is given lambda by mu square 2 divided by 1 minus lambda by mu. So, this is 1 by 8 into 8 by 10 square divided by 2 1 minus 8 by 10. So, that means 1 by 5 hour. So, it becomes 12 minutes. Okay. So, therefore, that you know, otherwise this becomes 12 minutes. Okay. This is the waiting time. Okay. This is if it is like that, and now here, now what happens, that waiting cost per trip in that case will be 1 by 5, because 12 minutes, that means in hour 1 by 5 into 300, that means rupees 60 per trip. Okay. So, this will be then the waiting cost will be rupees 60 per trip. So, basically loss will be rupees 60 minus 50, that means rupees 10 per trip. Hence, the management should not opt for new unloading system. So, new unloading system in this case is not justified. Okay. So, this type of thing we can do. We use a technical term, we say service level. Service level means that what is the quality of the service. That means, if people take more time in waiting, then service level will be poor, and if they take less time in the waiting, then service level is better. Service level is a function of two conflicting costs: cost of offering the service to the customer. That means, if you open more channels, you can actually do that very good, you can satisfy the customers, but your cost will keep on increasing. And another one is that cost is also there, cost of delay in offering service to the customer, because if you delay it too much, then the customer may become dissatisfied, some customers may leave this thing. So, that maybe this cost of offering the service to the customer is just the question of opening one more station, more operator, more machine. This can be easily calculated, but cost of delay in offering service to the customer is not easily calculated. That means, you should have common sense, because customers may show their dissatisfaction, but you have to convert that dissatisfaction into monetary terms. How much you get the loss and all those type of things, how much you will be this one. So, these numbers have to be calculated, that much work has to be done by industrial engineer, and then you can use the mathematics. Hence, an optimum service level that must be maintained by a queuing system can be determined by determining the optimum level of service rate. So, an optimum service level that must be maintained by a queuing system can be determined by determining the optimum level of service rate. That means, how much I should have my service rate. Basically, you can talk in terms of the service rate, and you should have more queuing. So, this rate should offer service and number of service facilities. That means, service rate can be increased by enhancing the service of that system, or increasing the server, in a way that avoids excessive delay in offering the service. So, that means it is like this. So, now let us say that let C1 is equal to cost per server per unit of time, that is cost per unit of time having a server available, and C2 is equal to cost of waiting per customer per unit time. TC is equal to total expected cost of waiting and service per time. Then the cost equation can be written as TC is equal to service rate into cost per service per unit time plus number of customers in the system into waiting cost per customer per unit time. So, how do you find out TC? Complete TC is equal to mu into C1. So, mu is the basically the service rate, and then cost per service per unit time. Suppose this is mu into, and this is about C1. So, mu into C1 will be the this one. If the service rate is high, then naturally that you have to pay more money to that. So, that is why it is mu C1. So, mu into C1, that means for unit mu, suppose the cost is C1. So, this is mu into C1 plus LS into C2. LS is the length of the system and multiplied by C2. That means more the length of the system, more the service rate mu, more money you have to pay. So, that is why mu C1, and more the length of the system, more this type of thing you have to do LS into C2. That is why you are getting LS into C2. So, for single server queuing model considering exponential service and unlimited queue, LS is equal to lambda by mu minus lambda. So, you can put that mu C1 plus lambda by mu minus lambda into C2. So, this type of expression has come. Now, how do you find optimum service rate? As service rate is measured in continuous units of time, the optimum value can be determined by taking the derivative of total cost with respect to mu and equating it to the 0 to identify the point of minimum cost. So, you can say dTc by d mu is equal to 0, or I can put d by d mu and in the bracket the complete expression mu C1 plus lambda divided by mu minus lambda into C2 is equal to 0. So, if you differentiate mu C1 with respect to mu, you get C1, and if you differentiate lambda divided by mu minus lambda with respect to mu, you get minus lambda C2 mu minus lambda square is equal to 0, and therefore, by solving this you get mu is equal to lambda plus under root C2 by C1 lambda. So, this is the optimum service rate which will balance both the things. You do not want to spend too much on the service also, and you do not want to disappoint the customers also. So, customers, now one example, suppose customers arrives at a service store on an average rate of 32 customers per hour. Currently, a single cashier serves customers at a rate of 40 customers per hour. The store owner estimates that every additional minute a customer spends in the system, including waiting and service time, results in a cost of rupees 5. An assistant can be employed to support the cashier at the rate of rupees 5 per hour, thereby increasing the total service rate to 120 customers per hour. Determine the optimal service rate in customers per hour that would minimize the total customer waiting cost, justify the requirement of an assistant. So, given lambda is equal to 32 customers per hour and mu is equal to 40 customers per hour, C1 is equal to rupees 5, and cost per additional customer service is basically rupees 5. So, waiting cost is equal to expected number of customers in the system into hourly waiting rate. So, expected number of customers will be lambda by mu minus lambda. So, it will be into 5, because this is the thing, and this is per hour because 5 per minute hai. So therefore that you know this will be this one, it is results in a cost of 5, okay, into 60 hourly waiting cost, okay. So that means this is equal to this one, it is written that including additional minute cost 5 rupees 5. So this is 5 into, that's why 5 into 60. So this comes out to be rupees 1200 per hour. So suppose it is like that, then new value of service rate is equal to mu is equal to lambda plus under root C2 by C1 by lambda is equal to 32 plus under root 1200 by 5 into 32, that means 119 customers per hour, okay, that much will be there. But that can provide the service of 120 per hour. It is written that if you employ assistant, then it can give you service up to 120 customers per hour. So it is better than that, means more rate. So that's why requirement is justified. That means you can put assistant and you can do that. Service levels can be discrete also, like a company operates at a customer service center where customers arrive at a rate of lambda is equal to 10 customers per hour, and the cost of customer waiting time is $5 per customer per hour. So suppose it is in terms of dollar, it is 5 customer per hour. The cost of providing service is $20 per server per hour. The service rate mu, that means customers served per hour per servers, can be increased by hiring more or faster servers, but this increases the cost. So you can say that objective is to minimize the total cost. You can make an optimization problem and you can solve that. You can say total cost TC is equal to service cost plus waiting cost. That means you have to combine these two things, okay. Expressions may differ case to case, but these type of thing, this is the basic. I am just telling the basic thing, and you can do that optimization problem. Total cost is equal to service cost plus waiting cost, and we can try various service levels. For example, we can do discrete way 5 customers per hour, then what is the situation? We can put 10 customers per hour, then what is the situation? Like that we can find out and we can see that whichever combination gives the minimum total cost. So this way we can actually complete that problems, and this is how that it can be done. So this way it can be these problems can be solved. So I just have given today the exposure of that economic factors in that, means giving theory, that one use is that management can use the giving theory to decide, take policy decision whether something will be economically justified or not. This type of thing we have discussed today, okay. So today we will do only this much, and now one more lecture which will be concluding lecture on giving theory, that I will be doing in the next class, and then this topic of giving theory will be complete. Although giving theory is a very wide topic, but we have taken simple case, and important thing is that Little's formula is very important, that LS is equal to WS by into lambda, and this is LQ is equal to, this is WQ into lambda, okay. So this is a very important formula, very simple but very important. So you, if somebody quickly gives you, somebody says length of this system, you can quickly find out waiting time in the system by dividing it by lambda. Similarly, somebody gives you length of the queue and you know the arrival rate, you can easily find out WQ. So this formula you should never forget. Okay, thank you very much for your attention. Okay, yes.